Do the video segment for chapter 7. This is a bent rod problem that we looked at earlier, but modeled it with solid elements. Now we would like to do that with beam elements. So the dimensions are given here, and let me start with making, and the cross section is a circle of a certain radius, radius 1 inch. Okay, so let's go ahead and create the wireframe model. So on a convenient plane, on that vertical plane, I will draw. You can go, remember, you can go, you can have two approaches. One is to create this thing in space, this wireframe or this wireframe in space, or you can create a sketch. But remember, if you're doing it with a sketch, you have to join it for sure. Okay, so let me make it as a sketch, something like that, and there. And let's put some dimensions here. So let me see, dimension from the top line to here. This is 8 inches. Okay. The radius of this corner is see now, it is 1 inch. All right. And then this dimension, the length from that point to this is 5 inches. 5 inches. Okay, because the cross section is circular, I don't need an orientation point. So let me, excuse me, let me join this. That's a requirement if you're going to go this route. All right, and then we apply material. Where is the apply material icon? I keep losing that right there. Let's make this thing out of steel, metal out of steel, and we close it. Okay, this is actually the model. So what do we save this thing? File, save management, save as, desktop, new folder, and I'm going to call it bent rod with beams. How about that? Chapter 7. Chapter 7. Okay. Incidentally, this problem does not have any planes of symmetry. This beam structure does not have any planes of symmetry that I can use. Okay. We now go to analysis and simulation, generative structure analysis. We are doing a static analysis, so say OK. All right, and this bottom point is clamped. Oh, actually, well, look, if I try to clamp this thing right now, it won't work because there is no mesh here. Okay, first you've got to mesh it. Okay, so where is the beam mesher? Right there. This is not the fancy beam mesher that is available in the advanced meshing tool. This is standard beam mesher. So you select this, and because I joined it, it's going to mesh the entire 3 segments. Otherwise, you know, you got to be careful. All right, good. If you want to look at the mesh, right-click Mesh Visualization. There we are. And notice that because I joined it at the interface, you have exactly the same node. So the interface between this curved section and the vertical section is node 2. Okay. I talked about these subtle issues in a previous video, which is also posted. All right, deactivate this mesh. Now the bottom can be clamped. This bottom is clamped. Now clamp means no display, no translation, no rotations. You could have done it with the user-defined restraint, so all 6 boxes should have been checked in that. This is the same as clamp for a beam or for a shell. This condition is the same as clamp condition, which I'm not going to do that. Just clamp it. Then we're going to apply a force, a displace. I have to define the cross section of this. So here's the 1D property. And this is the section that we're going to define the property. So click on the wrench. It's cylindrical beam, which means the cross section is circular. You click on it, and then the radius, I think the radius is 1 inch according to what I have in the description of the book. Just a fat beam. Okay. And you can close it because this is circular. Finally, I'm going to put a load here, the load at this point, just a point. Don't put it on that edge because it will not give you a concentrated force, but in the right direction. Now the right direction is, let me see now, in this particular drawing, direction X, because I want that thing to basically torque. In the problem, I don't know whether the force was specified. Let me see for a second. Uh, let's see, user defined. Yeah, I think in the book I'm applying a load of 2,000 pounds. Okay, so that'll be in the X direction, minus 2,000 pounds. Okay, good. If you look at it, it's exactly the way it should be. All right. Now, don't forget, before you run it, we're almost done. Before you run it, make sure you go and save the analysis file. Remember, on the exam, you have to give me not only the part, but the analysis file, both of them. If you're doing an assembly, which you're going to do in a couple of weeks, you not only have to give you the product, you have to give me all the parts that make that product and the analysis file. It's going to go in the same folder. Analysis is going to go in the same folder. And then run it. It's a very simple problem. There we are. And now you can look at the deformation. There it is, and you can animate it. Notice that this top portion goes through bending. The bottom portion, the vertical one, goes through bending and torsion. Now the deformation is correct, so let me looks reasonable. Let me look at the numbers. So these are the displacement. Now I told you that the graphics card on my computer gives you a horrible description when you say plot as average ISO. This will not happen to you because this is all wrong. This is all wrong. So I don't want to do it like that. Let me send it back to I think it's text or symbols, right? Back to symbols, right there, back to symbols, and the biggest displacement is, as a vector you can see it, is at this tip, this is the tip, and it's 0.0 in the direction x minus 0.04, so this is about, I don't know, 25 times bigger than the displacement in y, and about the same factor bigger than displacement. This point will displace in direction x, y, z, but the primary displacement in direction x. Now with Catia's beam element capabilities, you cannot plot the von Mises stress, you can plot the principal stresses, but the only principal stress that you're going to get for a beam is going to be the axial one, which is totally useless here. Okay, and it's all going to be, I mean, basically, there is some axial because of the fact that this is a bent rod. There is some axial principal stresses in this structure, and you can see that some are compressive and the other one are tensile. The tensile ones are, well, it looks like these are all compressive, but anyway, it's useless. I mean, these are numbers that they're all compressive. All right, so I'm going to stop here, and then I will start the tutorial with chapter 8.